So, okay, now the implicit function theorem. What is it about? Well, superficially, it's different from the inverse function theorem, but this is sort of a sister theorem. As you're going to see, once you know how to prove the inverse function theorem, this one is not so hard. The motivation is very different, and here's what it is. So, I have a function from a product of Banach spaces to another Banach space, right? So actually it's going to be a subset here. But for the time being, you can think that I have a function for v times w, right? So okay, let me write it properly. U contained v times w. This U is going to be open as usual to w. And we're interested in the set of pairs x and y such that phi of x and y is equal to c for a given c, right? So c is just an element of w. In these sets, well, there's one of them for each of them. So assume temporarily that v's are d and w's are k. So this Cartesian product, you can very easily convince yourself that's like our d plus k. And what you're looking at is, okay, phi has k coordinates, right? That takes values in rk. So each one of these coordinates is a function of these d plus k variable z. And I'm setting here an equation. So this is the ith equation. Say the ith coordinate of phi computed z should be equal to the ith coordinate of c. So it's just a list of equations in d plus k unknowns, right? Which are the coordinates of z. K equation is d plus k unknowns. Of course, we understand these things very well from the point of view of linear algebra. When phi is a linear function, what happens if phi is nonlinear? So actually, I want to add a a page here. Right, so suppose I have a linear system. So I have here z1. Okay, remember that I'm interested in the setting where I have a Cartesian product. So I have z in rd plus k. And I'm going to write z as having the first coordinates equal to the coordinates of vector x. And the last one is equal to the coordinates of vector yk. And then I have an equation like a times z, so that's a linear equation, equals c. And of course, A is a matrix that I'm going to write like this. Let me write this kind of y1, yk. And here I have my matrix with d plus k columns and d rows and k rows, sorry. This is A. That's here I'm thinking about the case where phi is really a linear transformation given by a matrix A. Here's a theorem for linear algebra. Of course, C is also a vector, right? The theorem is this. So suppose that the last k columns are linearly independent. If you don't remember what that means, well, look it up. Suppose these columns are linearly independent. Then, for all choices of x and Rd, either the system has no solution with or there exists a unique y and rk with z equals xy solution. There's a factor in linear algebra that if you have this non-degeneracy condition, then basically you're saying this. So as long as there is one single solution, one given x, if there is a choice of y for which you have a solution, you have this identity here, then for that's unique choice of y. So in other words, you can say, well, there are certain vectors x for which there exists a solution. Over these vectors, the y can be chosen as a function of x. Okay? So that's just linear algebra. It just comes from the fact that if I fix x1 up to xg, then this transformation from y1 to yk to c1 to ck is a linear transformation from Rk to Rk. If the columns are ID, then this linear transformation is invertible, and I can invert it. So, no big deal. This invertibility business is actually quite important because this, we're going to see now, a nonlinear generalization. So you can think of, right? So this is just for linear systems with G plus K unknowns and K equations. And we have this non-degeneracy condition about K columns being linearly independent. I'm going to tell you about the abstract version of that, which holds for any nonlinear function. So remember that phi is a function from an open set in V times W. And I'm going to define, right? So remember that the elements of the space here are like pairs, which I'm usually going to write as HV, HW, or XY, or something like that. So say I have X naught and Y naught in the preimage of C. So it's just X naught, Y naught belong to U, and phi of X naught, Y naught is equal to C. So I'm going to define a kind of second partial derivative of this mapping in the Y naught variable. How do I do that? Well, it's actually simple. The second derivative takes a vector in W and maps it to what happens. I take the first derivative. Well, the first derivative is a linear transformation from V times W to W. And I apply this linear transformation to the vector 0V HW. So in fact, D2 phi X naught Y naught is a linear transformation from W to W. And here's the non-degeneracy assumption I'm going to need to prove something like what I just said for linear systems. I'm going to assume that this linear transformation, which is a continuous linear transformation from W to W, is invertible. It has a continuous inverse. So in matrix terms, if we were to write this down, right, if phi is given by a matrix, if V's are D and W's are K, and phi is given by a matrix, you'd get exactly this condition from this non-degeneracy assumption. So it's really the same thing, except that now I have phi that's potentially nonlinear and lives in infinite dimensions, so there are all sorts of differences, but morally speaking, it's the same thing. Okay, what's the implicit function theorem? It's like the inverse function theorem in that it's a local theorem. But the local theorem now says something similar to what we said about linear systems. That is that if your linear system is non-degenerate, then the y coordinates can be written in terms of the x coordinates for all solutions. Or, okay, let me say it a different way. Suppose I have a point in here in U, contained in V times W. Suppose that the second derivative is invertible at this point. And let C be the value of phi of x0, y0, right? So x0, y0 belong to the preimage of C for a certain C and W. Then what I claim is that there's an open neighborhood of x0, y0, or x naught, y naught, or whatever. There's okay, forget about this A for the time being. Basically it's this. So if I look at this open neighborhood, the intersection of that with this phi minus 1 of C, the set of solutions to my nonlinear equations, this intersection looks like the graph of a function. So that's what's over here. So what's the graph of a function? Well, let me draw it schematically, pretending that V is here, W is here. The graph of a function is I take the A here, I draw the graph, and I have this set of pairs, right? So graph of G is just a set of pairs X, GX, where X belongs to A, and this is a subset of the Cartesian product of V times W, like in this graph here. So a graph, by definition, is just a subset of the Cartesian product with this structure. And basically, we're saying that as long as you have this non-degeneracy condition, then the preimage of C, the set of solutions to the certain equations, it looks like the graph of a function. Meaning, it's like saying, okay, I have a pair, phi, x, and I want to put something here so that I get c. I know that what I put over here is just the value of a function of x. So there's a unique choice of y to give the solution. So that's what the implicit function theorem says. It also says this function g is C alpha, defined over an open subset of V, but that's not too important. In any case, let's prove this theorem. As we're going to see, we're going to get it through an application of the inverse function theorem from our previous video. How do we do this? So if we try to apply the inverse function theorem, we sort of stop at at step 1, because in order to apply the inverse function theorem, you need a function from a subset of a Banach space to that same Banach space. And here, phi is a mapping from V times W to W. So these spaces are not the same. So potentially V times W is higher dimensional, much more complicated than W by itself. So here's how we define a function capital F that's related to phi, but maps V times W to V times W. It's actually quite simple. So it's like, okay, loosely speaking is this. So phi maps a higher dimensional space, V times W, to W. So I know it's not going to be invertible because, again, if I'm looking at finite dimensionals, I have more knowns and equations. So that's an underdetermined system of equations. However, if I expect that because there's a non-degeneracy condition, if I tell you what x is, and if I tell you phi of x and y, that is if I tell you c, so to speak, you can tell me who y is. So f is just going to be this function that tells me not only the value of phi of x and y, but also the value of x. And as we're going to see, this function is, you can apply the inverse function theorem to it. So there's a little exercise that you have to do, which is to look for the for sure derivative of capital F. And it turns out it has this form. So you apply it to a pair of vectors in V times W. So what you get is the first coordinate. The first coordinate is just a linear transformation. So it's just the linear transformation, the identity linear transformation itself. In the second coordinate, you get the derivative of phi. And you can actually repeat that with the higher derivatives to argue that since phi is C alpha, F is also C alpha. So this is something you need to check. I'm not going to do it for you. I can do it in class if you like. Now there's a little bit more structure here. Because remember that I assumed that the second derivative is invertible. Okay, let me remind you that if I look at this derivative here, what is this? Okay, this is a linear function, sorry. I'll apply it to HV, HW. Sorry, apply to watch. So I'm just gonna say it can take HV0W plus 0VHW. Right, the sum of pairs just gives me this pair here. And I can now use it here. So remember, okay, let me actually erase this and write it slowly with you. d phi of x and w, x or y, apply it to HV, HW. I'm just going to use, well, the Cartesian product, the vector operators is just coordinate by coordinate, right? So I can apply this 0w plus g phi x, g phi, this is x naught, y naught, x naught, y naught, g phi x naught, y naught, apply it to 0v, hw. So the first term is g phi x naught, y naught, hv 0w plus, well, this is our friend d2 phi x naught y naught applied to hw. That's the definition of d2 phi. And d2 phi, I just called it s to make life a little bit easier. So that's s applied to hw. So, okay. df, if I just go back to the formula, right? So let me go to it here. This derivative of f, I can go back here, I can rewrite it as first coordinate is the identity mapping. Second coordinate, there's this part that's like the first partial derivative. Second, applied to this 0 w plus s applied to hw, or sorry, the d2 phi xw applied to hw. And remember, I want to apply the inverse function theorem, so I need to prove that this thing, this derivative of f, is invertible. So now, actually, let me add a page here. Yeah. Okay, let me argue that. So df x naught y naught applied to hv hw, that has a form hv, then some linear operator applied to hv. This is supposed to be, sorry, this is supposed to be this part here, a applied to hv plus s applied to hw. So how do you invert this linear mapping? Okay, I'm just going to define u of a pair qv qw. So I want to define the inverse, right? So with the first coordinate, I don't need to do much. I get, well, whatever I put in, I get out, so that I don't need to invert it. Now, here's what I want to do. I'm going to take the second coordinate, so I want to get back hw. So what I do, okay, I take s minus 1 qw minus s minus 1 times a times qv. So I claim that if I, okay, call this operation here on top, I don't know. Oh, see, we use a bad name, sorry. This is T1 and this is T. So what happens if I apply T1 to T of HV, HVHW? That's like T1 applied to HV, AHV plus SHW. And that's going to be, well, HV S minus 1 applied to AHV plus SHV, right? So HW, sorry, I'm just using this formula here. Minus S minus 1 AHV. So this is exactly equal to HV HW. Therefore, we've argued that T1 times T is the identity operator on V times W. And also that you can check, T applied to T minus 1 is the identity operator of V times W. Now there's additional work you need to do, right? I'm trying to show that this linear operator is invertible. I've told you this is the inverse. You just check it. You also need to check this is a bounded linear operator. Well, there's a little bit of work here, but not too much, right? You're just saying, okay, you can bound the norm of what's here by something like, okay, 1 plus the norm of s minus 1 plus the norm of s minus 1 times norm of a. So, okay, I consider that it's been proven, modulo some details, that this operator is invertible. Now remember that we already know that f, right? So f is C alpha. I said, well, that's something you need to check, comes from the fact that phi is C alpha. And now he has invertible derivatives, so I can apply the inverse function theorem. That's over here. Inverse function theorem. to say, okay, there's a neighborhood of the point where you start, where f is a diffeomorphism, right? There's an open set. Now, I have an inverse function. Let's look at what it looks like, right? So f of x and y, well, it's just x and phi of xy. So if I invert that, if f inverts this, it does nothing to the first coordinate. Well, everything that happens sort of is in the second coordinate. And we know the inverse function is C alpha, so this h, well, it's a little bit of an exercise again, but h is C alpha. Okay, so let's look at this, right? So what is this guy? Phi minus 1 of c times u0. What is this? So it's just the set of points x, y, in u0 such that phi of xy is equal to c. Now, by definition of capital F, that's just a set of pairs such that f of x and y is equal to xc, which is just a set of pairs for which, well, look at the inverse function, right? Remember that f minus 1 of xc is x h of xc, right? So requiring that the pair satisfies this is the same satisfying this. Now I'm almost done because I'm kind of saying here that, okay, fix c, y is a certain function of x, and this function is what I'm going to call g of x. I just need to be a little bit careful and to check, okay, if I take a point x in V, if there exists a y in W such that xy belongs to this set, phi minus 1 of c intersection u0, what does that mean? That means that xy has the form x h of xc So in order for this to be true, it must be that the pair xy satisfies this condition here. Therefore, that can only happen if x and c, right, remember that u0 is mapped to u1. So I'm arguing, okay, that if I have a pair xy here, phi minus 1c, it must be that xc is in here. And vice versa. If xc is in here, it's because it's the image of somebody here. Okay, that's just using the fact that capital F is a diffeomorphism. So everybody here must have an image here, and vice versa. Okay, so now I'm basically done. So I define A to be the set of all x's in V such that the pair xc belongs to U1. I define G to be the function that takes x and L in A and maps it to h of x and c, right? So this is, you should write it as blue, this is g of x. And I'm saying this, so suppose x belongs to A, right? So xc belongs to u1. Therefore, there exists a y such that xy belongs to u0, and y is equal to h of x and c, so y is equal to g of x. And vice versa, if xy belongs to u0, then I get that xc belongs to u1, so x belongs to this set. And therefore, I have everything I need. Remember that my goal was to argue that phi minus 1 of c is 0. Let me write it again, right? So xy in u0 such that y is equal to h xc. I claim this is the same thing as x g of x, right? Remember this is g of x, where x belongs to A. And again, because G is C alpha because H is. And that's the end of the proof, because that's what we wanted to show. We wanted to argue that locally, see, around this neighborhood of x naught, y naught, phi minus 1 of C, the preimage of C under phi, the set of solutions to the equation phi x y equals C. Well, this set has a form of a graph of a function. We just found the function is C alpha as we wanted it to be. So yeah, this is a bit tricky, but you can check in a finite time. Let's put it this way. It's just the inverse function theorem. Now, of course, the key step is that because we know that this D2 operator is invertible, it turns out that DF, even though it's very different, is invertible too. So DF is over here. And given that this guy is invertible, this whole thing is invertible. And then we're done. Okay, that's the end of this video. There's a lot going on with the inverse and implicit function theorems. There are, of course, all sorts of applications of these things. We're going to be especially interested in applications to the manifolds. So that manifolds, introduction to the theory of manifolds is going to be the last topic of this course. And we're going to see that on the one hand, the inverse function theorem allows us to talk about the tangent space, to describe the tangent space of a manifold. The implicit function theorem gives us what's perhaps the easiest way to define manifolds. So in the end, under a simple condition, a set of finite, whatever a manifold is, I haven't described it, but a set of this form is always going to be a C alpha manifold if phi satisfies certain easy to check conditions. Okay, so that's it. Thanks again.